So is my screen is visible now? Anyone can confirm?
Not visible, sir.
Yeah, this one. So I'm writing something.
No, okay, sir. No, okay.
Okay. So we'll go to design the operation amplifier. Op amp design. What is the op amp? Op amp is a high gain amplifier. High gain amplifier. So I know. So this is the this is the symbol of operation amplifier. It's looking like this. It's looking like this. So this is the symbol of op amp. I think it is having two terminals, input terminals. One may be a positive, and one more may be a negative. Okay. Similarly, it is a output terminal. Output terminal. Okay. So, what is the operation amplifier op amp circuit? Internally, what circuits it is having? What is the equivalent? What is the internal circuit? Internal circuit may be a I can say one we have one differential amplifier. So differential amplifier means the differential amplifier. Differential amplifier. So of course, differential amplifier has the two inputs. And the next stage of the differential amplifier may be a one more gain stage. One more gain stage, because the differential amplifier gain, whatever the gain produced with differential amplifier, is not as much as high. So that one more gain stage is required. Gain stage. Okay, so the output of the gain stage, and another third stage is I think buffer. Buffer stage. Okay, got my point? Hello?
Yes, sir.
Yeah, so then yes. Okay, so without this buffer amplifier, without this buffer stage, I think it is a suppose if you not consider the buffer amplifier or buffer stage, then it becomes the only OTA. What is the OTA? OTA means, so without buffer, you can call it
Operational transconductance amplifier.
yes. So it's called the OTA. Okay. So why the differential amplifier is first actually, suppose if we need 100 dB gain, 100 dB gain amplifier, 100 dB gain amplifier. Your differential amplifier will not produce, okay, will not produce so that much of gain. Mostly your differential amplifier will 1 minute. Yeah. So without this buffer, you can say this is the OTA. And suppose if you want 100 dB gain, 100 dB gain. So for let us say example, for example, your differential amplifier, this differential amplifier maybe produce only 50 dB gain, 50 dB gain. This is my assumption because a differential amplifier, I think it is a maximum it can produce less than 50 dB gain. Okay, so that so because the requirement of the amplifier is 100 dB gain, but differential amplifier will give the only 50 dB, and one more 50 can be produced by the another gate stage, another gate stage. Okay, so that I can first of all I will discuss about what is the differential amplifier design. Differential amplifier design. Okay, so later we'll go to the another design. Okay, so how to design the differential amplifier. Okay, so first of all, differential amplifier design. Okay, so what is the differential amplifier design? First of all, we'll see. So for design of the differential amplifier, some requirements are there. What requirements? So that means the designer should give the some design requirements. So we can say the requirements or spec. You can say you need to design the differential amplifier with some specifications. I will write the specifications here. Those are the requirements, specifications. One minute. Okay. Specifications. Specifications are first one. So UMC, UMC. 1 minute. Okay. Specifications. Okay, these are my specifications. Okay, so then first one, UMC 180 nanometer process. UMC 180 nanometer process. Okay. UMC 180 nanometer process or technology, you can say. That is the specification. Second specification is VDD is equal to. So generally, for 180 nanometer process technology, VDD value will be 1.8 volts. 1.8 volts. And the voltage gain AV is greater than or equal to 100. When you are going to convert, 1 minute, when you are going to convert, now voltage gain AV is greater than or equal to 100. Suppose if you convert into the dB, then what is that one? What is the equivalent value in dB? 20 log 100 is equal to how much? Anybody can tell you? Anybody? So it's maybe 40 dB. Am I correct? 40 dB. Okay. Okay now. So
Yes,
another specification is load capacitance. CL, C suffix L, load capacitance value is equal to 10 picofarads. 10 picofarads. Okay. Okay. One minute. There it is. Is it visible? Hello?
yes, sir.
Yes, sir.
Good, sir.
Yeah. Yes. So then, fifth one is So fifth one is one more specification is ICMR. Maximum ICMR. I can write it as a ICMR plus. So ICMR means input common mode range. Its value is 1.6 volts. So then minimum ICMR, minimum common mode range voltage, I can write it as ICMR minus is equal to 0.8 volts. So then, so another one is slew rate. So I think you know the definition of the slew rate. Definitely I will tell you later. So its value is 5 volts per microseconds. Okay. So another one is power dissipation. So power dissipation is less than 0.3 milliwatts. So one more thing is gain bandwidth product. Gain bandwidth product should be greater than or equal to 5 megahertz. Okay, these are the specifications. So with this specification, we should write the what is it? We should design the your differential amplifier. What do you mean by design? Design means what is the meaning of the design? Hello? Anybody know what is the design? చెప్పండి లేదు తెలియకపోతే చెప్తా ఏం ప్రాబ్లం లేదు. What is the design? Design means so finding all the transistors so W by L ratios in the circuit got my point? Hello Ramani garu
Sir, వింటున్నా సార్
అదే
అర్థమైంది
what is the
sir.
meaning of the design? Design means finding the W by L ratio of all the transistors in the circuit. Okay.
Yes, sir.
Okay. Okay, these are the specifications. Okay, now, so you can do one thing. You can draw the schematic of the circuit diagram of the differential amplifier. So differential circuit diagram. I think you know everybody knows about the differential amplifier. So once again, I'm going to draw the differential amplifier circuit diagram. Here is one PMOS transistor and one more PMOS transistor. Okay. Yes, this is the M3 transistor. This is the M4 transistor. This is the VDD. Okay. And This is the differential pair. Here is differential pair. So this is M1 transistor. This is M2 transistor. This is the positive input terminal, V in positive, V in plus. This is the V in minus, and there is a tile current source which can be designed with a current on a transistor M5. And this is biasing voltage for this M5 is set by one current source. This is the M8 transistor. This current source is I0. This current source is I0. Okay. This is so this current is also, since this is I0 current is flowing this one. This also I0 current. Since I0 current is flowing through the M5, and this is this branch and this branch both are, this branch and this branch both are symmetrical, and this branch carries the current of I0 by 2, and this branch carries the current of I0 by 2. Got it? Hello?
Yes, sir.
Yeah. So this is the output you are going to collect here. Output. So the output is collected. You can take from one capacitor, load capacitor, CL. This is the V0. Okay. This is the differential amplifier. Any doubt? Hello?
No, sir.
And we will call this differential amplifier as the single stage operation amplifier. Single stage operation amplifier. Single stage or one stage op amp, you can say. Op amp. Yes. Got it? Hello?
Sir.
Yes.
Yes, sir.
So now, so because of symmetry, symmetrical this side and this side, the symmetrical configuration, because of symmetry, so M3 is equal to M4. What do you mean by this one? Both the transistors are equal dimensions. Similarly, M1 transistor and M2 transistor both are symmetrical. Got it?
Yes, sir.
So since they are symmetrical, you can take like this. Okay. Next, see, first of all, so this is the operation amplifier. Okay, amplifier has the stages: differential amplifier and gain stage and buffer stage. So we are concentrating on the only first stage, that is called the differential amplifier. Sometimes differential amplifier is called the single stage op amp. Okay, got it? Why the single stage op-amp will give the very less gain. That's why another gain stage we want to connect to this one. Okay. So how to design the differential amplifier? What is the differential? Where is the differential amplifier circuit? I think here is the differential amplifier circuit. Yeah, this is the differential amplifier circuit. So how to design this differential amplifier? So design of the differential amplifier means, so finding the W by L ratio of all the transistors in the circuit. M1, M2, M3, M4, M5, M8. All these transistors, W by L ratio should be found. Okay. So for design of this operation amplifier or single stage operation amplifier, we need the what is that one? Specifications. So what are the specifications? He given some specifications like technology is 180 nanometer and VDD value is 1.8 volts. Voltage gain is 40 dB and CL value. CL means what? Load capacity value is 10 picofarads. Okay. So similarly, ICMR, maximum ICMR is 1.6 volts and minimum ICMR is equal to 0.8 volts. Slew rate is equal to 5 volts per microseconds, and the power distribution should be less than 0.3 millivolts, and gain bandwidth product is 5 megahertz. These are the specifications has given to design the what? The differential amplifier or one stage what? One stage? Yes.
Differential amplifier.
Yeah. So now we'll start the design. So design procedure I will write here. Design procedure. Design procedure. So the design procedure is, first of all, find I0 value. What is I0? I0 is the current, reference current source value. Okay, I0, which is nothing but the DC current, DC current from slew rate. That is the first step. Second step is find, okay, M3 and M4 dimensions, okay, dimensions or W by L ratios, of 3, 4. Okay, so from maximum ICMR value. And third step is find M1 and M2 W by L ratios, okay, from gain bandwidth product. And the fourth step is find M5. So W by L ratio from minimum ICMR value. And next step is find M8 transistor W by L ratio, okay, from I0 and M5. Got it? This is the procedure. Understand?
Yes, sir.
Yeah. So now I will start step-by-step procedure. Okay. So I will take the first one. That is what? So finding I0. So I0. How much? Okay. That is the first step. So I think how to find the I0 value, DC current value from the slew rate. Okay. What do you mean by slew rate? Slew rate is nothing but maximum rate of change of output voltage. Maximum rate of change of output voltage V0. So if you take this circuit, if you take the circuit, yeah, to take this circuit. So here in this circuit, 1 minute. So in this circuit, this is the load capacitor. Okay, and assume one side is suppose yeah. So the CL will be charging like this direction. Okay, the charging through M4 transistor and discharging through M2 transistor. Once it's fully charged, so this is the output. Node voltage is output voltage V0. So how the voltage V0 quickly rise and falls? How the voltage V0 at this node, the node voltage at the V0 will rise and fall. So because of the CL value, because of the capacitor charging and discharging, the V0 value may be rising or increasing or decreasing. So whenever you are talking about the slew rate, whenever you are talking about the charging and discharging of this capacitor, assume that one side is completely off. Okay, and assume this side is only on. Clear? Understand? So I will once again, if you take this the circuit, same circuit. What is the CL? CL is the load capacitor. CL is the load capacitor. Is the load capacitor. Load capacitor, which will charge, which charges through which transistor? M4, and discharges through M2. That's it. Got? Okay. So if you take the same circuit, this is the M4 transistor. As I told you, it will be charging through this transistor like this. This is the capacitor, yes, and this is the node voltage V0. This is CL, and this is the charging direction, and discharging direction is through M2. So that this is M2. This is M2. Okay. This is M4 and M2. Yes, discharging is like this direction. Got it? No? So then I can write the slew rate. Slew rate is equal to, so the maximum rate of change of output voltage. What is output voltage? V0. So the rate of change of output voltage V0 is, this is the slew rate. Okay. So what is the charge across the CL? Charge, you can write Q is equal to C into V. Of course, C into V means CL into voltage V0. Voltage V0. In place of V, I can write what is the dq by dt I want to find. This is the V. Okay. So dq by the rate of change of, or rate of charge, dq by dt is equal to, so you can differentiate this. CL is multiplied with dV0 by dt. dV0 by dt. dV0 by dt. dV0 by dt. Understand?
Yes, sir.
What is the dq by dt? Is nothing but the current. I can say I0 is equal to CL CL is multiplied with what is the dV naught by dt? Here is there. What is this? Slew rate. Got?
Yes, sir.
Yes. So now slew rate. Okay, so go to the specifications. Go to the specifications. So what is the CL value is given? What is CL value? 10 picofarads is given. Okay. Into what is the slew rate is given? 5 volts per microseconds. 5 volts per microseconds. If you multiply these two, then what is the I naught value got? 50 microamperes. Got it? Hello? So that first step is the finding of I naught value. So to find the I naught value, we need slew rate. Okay. So slew rate is equal to dV naught by dt. Okay. That means the rate of change of output node voltage with respect to the time. So Q is equal to CL into V. So if you differentiate it with respect to the time, then CL into dV naught by dt. So dQ by dt is the I naught, is equal to CL is multiplied with the dV naught by dt is the slew rate. So CL value is given in the specifications, that is the 10 picofarads, and the slew rate is 5 volts per microseconds. Any doubts? First step? Hello?
Sir.
No doubt, sir.
Yeah. So when we go for the next step, okay, that is the what is the next step? So that is M3 M4 W by L ratio of 3 and 4 transistor we want to find. Okay. So what is the requirement for this one? Yeah, ICMR plus is the requirement. Okay. So what is the ICMR? We'll see. What is the maximum ICMR? ICMR plus. What is the ICMR? So see, if you draw the one side, this is the this is the M3 transistor. So M3 is the PMOS transistor, I think. Yes. Drain connected. Yeah, next one is this is the M1 transistor. Okay, so this is the NMOS transistor. This is the VDD. This is the source. Yeah, this is the M3, M1, and this is connected to the M5 also, so that I can write this voltage is V1. Okay, and for this M1 transistor, we are giving the Vin plus. Got it? And this node is, you can say Vx, node voltage is Vx. Any doubt? The circuit? Hello?
No, sir. No, sir. Got it.
Tarun? Tarun?
Sir. Sir.
Yeah. Understanding or not?
Yes, sir.
Yes. Pavani? Pavani,
Sir.
are you understanding? Okay, Joshna? Joshna? Okay, see, what is the meaning of, I'm talking about the ICMR, input common mode range. So one thing I forgot to discuss with you, before going to design, okay, before first step, So we need to understand, we need to assume all the transistors, all the transistors in the circuit, are in saturation, or in saturation. That's it. Understand? This is a very important thing. This is first assume this one. Everyone in the transistors, every transistor in the circuit are in saturation. Okay, so when it comes to this ICMR, that means input common mode ratio, what is the maximum value? Maximum value, the limit of maximum. So means, suppose if ICMR is applied to the gate of this M1 transistor, okay, so that one condition should be satisfied. That is what VDS should be greater than VGS minus VTH. What is this condition? Saturation condition. So suppose if you take the M1 device, Vx is the VDS of M1, and VGS is the, of course, this voltage is VGS, and VTH is this device threshold voltage. So if this condition is true, then the device M1 is in saturation, M3 is also in saturation. If this condition is false, so any one of the device transistor in the circuit forced into the triode region, so that how much maximum voltage it can be allowed to satisfy this condition. If you give more than whatever the maximum value is given, then definitely M1 forced into the triode region, and later M3 may be forced into the saturation, triode region. Then this condition becomes violated. Got my point? So input common mode ratio is the maximum input common mode ratio is the voltage, the maximum voltage applied to the gate of M1, which will keep or which will not disturb the saturation of the other transistors. Got my point?
Yes, sir.
Hello? Yeah, that is the input common mode maximum. Maximum value means you should not, you cannot apply more than whatever the allowed value. Because if you apply, what is the value is given for 1.6 as given. Okay, 1.6 voltage, 1.6 is given. ICMR maximum. If you give 1.7, then M1 enter into the triode region, thereby M3 also enter into the triode region. Okay, so that all the transistors must be operating in the what region up to saturation only. Okay, so that okay, anyhow, so I can write here if V in positive, V in plus is for greater than ICMR plus, ICMR plus, what happened? So the devices will enter into the M1. So M1, okay, will go into the triode region. Triode region. So that's why you should not apply more than that value. Okay. So anyhow, so as per this condition, yeah. So VDS should be greater than VGS minus VTH. VGS minus VTH. Okay. So now, so VDS means the drain voltage of M1. You can say drain voltage of M1. So is the VD. You can say VD is greater than. So VGS means you can say VG minus VTH1. VTH1. Okay. So what is the VD value? VD value is nothing but Vx. So that Vx, okay, it should be greater than or equal to Vz. Vz means what? Forget what is applied. Vn plus. Vn plus minus VTH1. VTH1. So that is greater than or equal to Vn plus is nothing but ICMR plus. ICMR plus minus, so VTH1. So that is greater than or equal to, what is the ICMR plus value is given 1.6 minus, for NMOS transistor threshold voltage maybe 0.45, you can assume 0.45, then 0.6, 1.6 minus 0.445 is equal to, that means Vx value. Vx is greater than or equal to how much? Is equal to 1.15 volts. Approximately you can say 2 volts. 1.2 volts, sorry. 1.2 volts. Got? So now see, this is the VDS3. This is the VDS3. VDS3. So VDS3 is equal to what is that one? VD minus drain source minus drain voltage. Okay, you can write VD minus, so VDD minus VDD minus, what is this voltage? Vx voltage. Vx. So VDD is 1.8 minus Vx, how much you got? 1.2 volts. 1.2 volts. 1.2 volts. Then what is the answer? 0.6 volts. That is the VGS3. Okay, so you know the so Vx value, thereby VDS value. Okay, these two are known. And one more thing is, what is the, how much amount of current is flowing through the M3 and M1 transistors? How much current is flowing? How much current is flowing?
I not.
By 2. Half of the I naught. Am I correct?
By 2.
Half of the yeah. So that the current flowing in this branch is, so I naught by 2. So I naught by 2. What is I naught you got? 50 microamperes.
50 microamperes. Sir.
By 2 is equal to 25 microamperes. This is the current flowing in the I3. That means I3 comma I1. Both are same currents. One. Okay. Got my point? The current in the M3 and M1 is 25 microamperes. Okay. Hello? Is it visible?
Yes,
Visible,
sir.
sir.
Okay. Yes. So now we know the So current I3 comma I1 we know, and VGS3 we know, sorry VGS VDS3 we know, and similarly Vx we know. Okay, so now saturation current equation we know. What is saturation current equation? Saturation current equation of either M1 or M3 is, I can write, so ID 3 comma 1. What is the formula? Half is multiplied with, so I think there are two transistors. M3 is the PMOS and M1 is the NMOS. You can write for anything, no problem. If you want to write for PMOS, so mu P COX, so W by L of 3 comma 1 into VGS minus VTH whole square. Am I right? This is the saturation current equation. Okay, understand or not?
Yes, sir.
Yes. So in this equation, we know this 25 microamperes. So of course we know this and this. The thing is, we don't know this and this. These two things are don't know. So we want to find them first. So they can be found to the simulation process. Okay. Suppose if you take for an NMOS, or PMOS, if you take anything. Suppose if you take the PMOS transistor, this is my PMOS transistor. Okay. If you simulate this, suppose 2 volts applied, and here is a yes current source. Okay, so this is the 50 microamperes. Okay, so similarly for NMOS, if you want to simulate, then this is my NMOS. This is plus minus VDS. This is the VDD. This is the 50 microamperes. This is okay. So from this simulation, you can find two things. One is the this is a PMOS. That's why mu P COX you can find mu P COX and beta P effective. So for the simulation of this NMOS circuit, we can get mu n COX value and beta n effective value also you can find. Yeah. So these are required because two equations we should take to solve the two what is that W by L ratios, of course. And one more thing. So we want through the simulations, yeah, we need, so this mu COX value is equal to how much, and also VTH also you can get from simulation. These two things you can find. Okay, for that avoid so lambda value. What is the lambda? Channel length modulation. And L is equal to take L minimum is how much? L minimum is equal to, because it's a 180 nanometer technology. L minimum value is 180 nanometers. That means 0.18 micrometers. 180 means this is the L minimum. So that's why I will choose the L value more than this L minimum value. It should be greater than L minimum. So that I can choose this value is 1 micron. 1 micron. Okay. So understand this one, these assumptions. Okay. Hello?
Yes.
Yeah. So now I will continue this one. So this second step is going on. Through the simulations, we got to the cadence in beta effective value. Beta P effective value is equal to 600 mu microns. Okay. So what is the beta P effective formula? Beta P effective is equal formula is equal to mu P COX W by L effective. All these terms are you can get. This is from the simulation. This is also you can have a simulation. This value is approximately how much you got? 600 micron. So here, so in this equation, we want to know this one because this is also through simulation. We got the 10 value. Okay, so into mu P COX 600 micron. So from this, so how much you get? Mu P COX value. Mu P COX value you got 60 micron. Similarly, to the simulation of the NMOS transistor, you will get the beta N effective value as 2.988 milli. Okay, so that this W by L effective value is same 10 only. So that you will get mu N COX into 10 is equal to 2.988 milli. So that is equal to mu N COX value is equal to 300 micro you get. Yes. Similarly, one more thing you can find to the simulation, that is the threshold voltage. So for the threshold to the simulation, you can get the threshold voltage VTHP is equal to 0.5 volts and VTH1 value. So VTH1. These are the to the simulation only you got. You'll get the 0.4 volts. Yes. Now, what is the I3 current formula? So I3 is equal to 1 by 2 mu P COX. So W by L. Okay. So W by L of 3. WL of 3. Okay, so WL of 3. What is the formula? Yes, VGS minus VGS3 minus VTH3 or VTHP, you can cite. Okay. So what is the I3 value? How much you got? 25 microamperes you got. 1 by 2. What is the mu PCOX value? How much you got? Mu PCOX. Yeah, 60. Yeah, 60. Here is 60. Yes, 60. So I don't know the W by L ratio of 3. Okay, since the symmetry 3 and 4 are same, and VGS3 value is how much? Already calculated. VGS3 0.6 volts you got. Okay, how much you got? 0.6 volts. VDS3 is what? VGS3. Okay, so that is the VDS3. This VDS3 is nothing but 6.6 volts. So what is this is the 0.5 volts threshold voltage. So now only unknown quantity is only W by L. Therefore, if you solve this, W by L of 3,4 is equal to, you will get 84. Got it? Hello?
Yes, sir.
Yes, this is the W by L of 3 and 4 transistors. Okay, so if you have some integer value, suppose 84 point something, fractional value, it should be always integer, because W by L ratio is nothing but width to length ratio should be always integer, so that approximate to the higher value. Okay. So what is the next one? What is the next step? Third step. Third step is M1, M2 finding. What is the W by L ratio of 1, that is third step. Okay. So to find the W by L ratio, how to find the W by L ratio of 1 and 2? Through the gain bandwidth product. Am I
Gain
correct?
bandwidth.
Yes. So the gain, yeah, for finding so M1 and M2 dimensions we need small signal model. Small signal model. Okay, suppose small signal model where? So at the output side you can take. So at the output side you can take small signal model, means this is, here you can take the small signal model for this part. For this part you can take the small signal model. Okay. So I am going to draw the small signal model. See, this is plus minus V in, and there is a whose value is GM2 into V in. Okay, and there is a resistor. Okay, this resistance value is R04, M4 transistor resistance is parallel with R02, and there is a load capacitor CL, and this is my output voltage V out, V naught. Are you understand?
Yes, sir.
If you want, yeah, if you want, I can go back and I can say here at this node. So at this node, okay, I'm talking about this one. Okay, CL is there, and what is the output impedance here? This is the R04 and this is the R02. These two are parallel combination. Can you agree with me? So for this, resistance is R04. For this, R02. These two are parallel here at this node. Am I correct? Okay. So then, yeah, find the transfer function. So here is, what is that? From this circuit, you can write the current, all branches. One current is what? This is one current. This is GM2 V in is the one current. GM2 V in is the one current. Plus one more current is through this resistor. So that V naught by current is R04 is parallel with R02. So plus one more current is current to the CL capacitor. So V naught by, so 1 by impedance of the CL is SCL is equal to 0. This is. Okay, so from this transfer function, find the transfer function V0 by V in is equal to, so you got, so after finding separating the V in terms and V out terms, then you will get minus GM R04 is parallel with R02. So divide with, who is that? So 1 plus S into CL. So R04 is parallel with R02. Okay. So what do you understand from this transfer function? So from this transfer function, you can say this is the single pole system. Am I correct? Single pole system. So if you want, if you draw the Bode plot, gain plot, this is the gain in dB, of course, gain, or this is the frequency, log omega axis, log omega axis. Okay, since it's a single pole system, you will get the gain like this, constant DC gain will get. This is the DC gain. This is called the DC gain. So DC gain. What is the DC gain in this equation? So whenever you're talking of the DC gain, this S is 0. S is 0 means you got only numerator term. That is GM into R04 is parallel with R02. That's it. So whenever one pole comes, only one pole is there, that is a P, pole comes, the slope is changing to negative. This is the minus 20 dB slope. And this is the what? Gain bandwidth product. This is the gain bandwidth product. This is. Got this? Are you understand? DC gain is how much? GM into R04 is parallel with R02. And pole 1, or only one pole is there, of course. So pole 1 is equal to, you can write 1 by, okay, what is that one? CL R04 is multiplied with R02. This is the pole frequency. Okay. Yeah, you should confirm it. Is it okay?
Yes, sir.
Yes. Any doubts, please? Ramani garu?
No, sir, vinnanu.
Yeah. So the next one is continuation of this one is, I think this plot, this is a single pole system. Okay, this plot, you know. So now from this curve, I can say gain bandwidth product is equal to formula DC gain is multiplied with pole. Sorry. Yeah, otherwise you can write like this, no problem. Is multiplied with pole. That's it. Pole. Yeah. Pole. So what is the DC gain you got? GM into R04 is parallel with R02. It is multiplied with the pole. What is the pole? Pole is here. 1 by S into CL into
1 by CL.
R04 is parallel with R02. Yeah. So then this and this get cancelled. Okay, what remains? So gain bandwidth product remains.
GM by CL.
Gain bandwidth is equal to, so GM by, so S into CL you got.
CL.
Got it?
Yes, sir.
Here is GM means what? 1, 2. 1, 2. Because M1, M2 both are same. What is the gain bandwidth? What is given? He given GB as the 5 megahertz is equal to, so GM 1, 2 by S means omega. Omega means 2 pi. 2 pi CL value. Okay. I think everything is known except GM value. So that you can find the GM value. So from this, your GM value, therefore, GM 1 comma 2 is equal to, after substituting CL value, you will get the 314.16 micro. Okay, understand? Now, what is the formula for the current equation? So I 1 comma 2, saturation current equation. What is that one? 1 by 2, both are NMOS transistors. That's why mu n COX. So W by L of 1 comma 2 into so VGS minus VTH square. This is the formula. Okay. So do one thing, differentiate this with respect to the VGS. Then what happened? So dou I d by dou VGS is equal to GM. So this is about the GM value. So GM 1 comma 2 is equal to, after differentiating, what you got? So mu n COX W by L into so VGS minus VTH. This is okay. Scaling both sides. Then GM 1 comma 2 square is equal to mu n, okay, COX W by L whole square into VGS minus VTH whole square. Yeah, again convert this into the right in terms of current equation. So in the current equation, what is there? 1 by 2 mu n COX W by L into VGS minus VTH. Square term is as it is. This time I can write that twice, and so by 2 is required, so that into 2 by 2, so that you will get, that is equal to, I can write this as mu n COX, okay, into so W by L into W by L. Okay, so 2 into ID, 2 into ID. This is, yeah. So what to do? So multiply the above equation into 2 and divide by 2, or multiply both the terms with the 2. Then it becomes like ID equation. So that this is, you know, the drain current ID. ID value is how much? So what is the current carrying? What is the current flowing into the M1 transistor? How much current is flowing? Already you know, I naught by 2, 25 microamperes. So that from this W by L of so 1 comma 2 is equal to GM square by 2 into so ID into mu COX, of course mu and COX. So from this you will get the 6.57 micron. That is approximately equal to 7 micron, because of W by L ratio should be integer value. Okay, understand? Or 7 you can write, because W and L both are using same dimension, so that you know only 7. Okay, understand?
Yes, sir.
Hello. Yeah, this is
Yes,
the next step is fourth step now.
M5.
So W by L of
5.
5. Okay, so how can you find the W by L ratio of 5 from the value? M5 can be found by using ICMR minimum value. ICMR minimum value. What is ICMR minimum value?
A civilization that is much older.
Yeah. So if you take M1 device, this is M1 device, for which you are applying the Vin or ICMR minimum value. So, and bottom you have a one transistor, that is the M5 transistor, and it is grounded. So M5. And this is the all are in saturation. That's why between this there is a VD saturation. VD sat. And the current flowing in this one is 25 micro amperes. This is the M1 transistor. And between these two, there is a voltage of VGS. Okay. Now, the condition is, what is the condition? Vin should be greater than, Vin means this is Vin is should be greater than, so VGS1 plus VD sat. So VD sat means the voltage at this point. VD sat means voltage at this point. Okay, so this plus this must be greater than. So that means Vin is how much? What is the ICMR value? Negative? ICMR minimum value? 0.8 or 0.6? Hello? ఎంత ఇచ్చండి? Yes, 0.8. So that 0.8, Vn is about 0.8 should be greater than VGS1. So VGS1. So VGS1 plus VDS sat 5. VDS sat 5. Yes. So here I want VGS1. What is the VGS1 value? So I want to find VGS1 value is how much? Okay. What is the drain current equation? So ID1 already you know is equal to 1/2 mu n COX W by L of 1 into, so VGS1 minus VTH whole square. Substitute all the terms. What is ID1 value? 25 micro is equal to 1/2 into this value is how much you got? So 300 micro, and W by L value how much you got? 7. So here is VGS. I don't know that I want to find VGS1, I can say, minus VTH value already we found 4/5 square. So from this equation you can get the VGS1 value as 0.6. Okay, now substitute this one here, then 0.8 should be greater than 0.6 plus VD sat 5. VD sat 5. Okay, so I think from this VD sat 5 is how much? Therefore VD sat 5 is equal to how much you got? Yes, VD sat 5 should be less than or equal to 0.2 volts. That's it. So now once you know the VD saturation, then what is the current equation? The M5 transistor, that's called the, I can write, so ID5 is equal to half mu n COX, so W by L of 5, and in this place you can write the VDS sat into VD sat 5. Substitute all the things to find the W by L ratio. From this already, what is ID5? ID5 is nothing but the current through the M5 is how much? 50 micro is equal to 1/2 into 300. So micro into W by L of 5 into 0.2. Yes. So from this, I think from this W by L of 5 is equal to, you got 8.33. Approximate is 9. Got it? Hello? Okay now?
Sir.
Yes.
Yes, sir.
Last one is M8. So W by L of 8 is equal to how much? Okay. Since what is the current flowing in the M8? Hello? What is the current flowing in M8?
ID. Sir. I not.
I not only. Okay. Same current. So M5 and M8 both are flowing, carrying the same current, same amount of the current. Since same current is flowing through, so M5 and M8, that is I0, that is equal to 50 microamperes. Okay, so W by L of 5 is equal to W by L of 8 is equal to same. Understand?
Yes, sir.
Okay, so this is the same. How much you got? This one, this value? So 9.
9.
So now you have all the transistor sizes. W by L of 1 is equal to W by L of 2 is equal to, how much you got? 7. So W by L of 3 is equal to W by L of 4 is equal to how much you got?
84.
84. 80?
84, sir.
84. Next, W by L of 5.
5 is equal to
W by L of 8.
is equal to 9.
So all the things you know now. Okay. So now with these ratios, if you design a circuit, okay, if you design a circuit in the Cadence software, then you can see the gain, how much gain you will get. Okay. So maximum you will get the gain. What actually he has given the 40 dB. So that only 40 less than 40 got. You cannot get more than 40 dB. But so my primary requirement at the beginning, I assume that I need a gain of 100 dB. So I think 100 dB gain cannot be possible with the single stage op amp. That's called the differential amp amp, because only I can get the 40 dB. So at worst case 40 dB I can get. If everything is fine, I can get the 40 dB. But mostly we'll get the less than 40 dB only. So where is the remaining 60 dB? So for that I need another what stage is the another stage is required. I want to add another stage. That's called the gain stage. One more stage I need to connect for this differential amplifier. Then this fellow will get 40 and the other fellow will get the maybe at worst case he may get the 40 or 50 dB. Then roughly the total may be the 100 dB. Okay, understand? So whenever the second stage is connected, then it becomes the two-stage operation amplifier. So now whatever the things we have design procedure discussed so far is only for the single stage op amp. Differential amplifier is nothing but the single stage op amp, only one stage. So one more stage if you add, then it becomes the two stage. Then gain becomes, you will get the more gain. Understand? Hello?
Yes, sir.
Yes, sir.
So I think this is the single stage op amp design. So in the next class I will explain the two stage op amp design. Okay, so now you can anybody can tell what any if you have any doubts. Yeah, if you have any doubts, please.
No, sir.
Hmm?
No, sir. Advanced bar.
Okay then. Okay, how can you get this? Okay, I will forward upload this video. If it is no doubts, I will stop here because two stage open will take again more than this time to explain. Okay, so that it is not possible to complete now. So in the next class, I will complete. So can I shall I stop here?
Yes, sir.
Yes.
Okay. So thank you.
Okay, sir.